Hello, welcome to my talk on Euler equation. In here, we will see the detailed explanation and the derivation of Euler equation. As we know, Euler equation is the fluid dynamic equation for inviscid flows. That means the Euler equation excludes the fluid viscous forces. In this talk, we will see why we need to study Euler equation, and we will see the fluid domain discretization and the fluid state, and we will talk substantial acceleration with a further explanation. Then we will have a look at the fluid dynamic equation with a discussion of the fluid dynamic equation. We will see the fluid body and the surface forces for the fluid dynamics. And lastly, we will have the Euler equation. Euler equation is the moment equations for fluid dynamics for inviscid flow. And the question here, why we need to study Euler equation since all fluids are viscous. The reason for this is the Euler equation is the first generalized equation for fluid dynamics. This is an extension of the Newton's second law of motion for point mass to the fluid motion. And the complete fluid dynamic equation, the Navier-Stokes equation, is based on the Euler equation, but only include the fluid viscous force in the equation. In reality, the most common fluids are the air and the water. Both fluids have very small viscous coefficients, and in many practical applications, these two fluids can be regarded as inviscid flows, as we have seen in Bernoulli's equation and potential flows. The Bernoulli's equation is the most used equation in fluid engineering, which is derived from the Euler equation. The very useful potential flow theory is working also with the Euler equation. In the Eulerian representation, the fluid domain is divided into many small regions, and on these regions, we will study how the flow passes the region, or what is the pressure in the region, etc. The fluid states indicated by the fluid velocity vector v, the fluid pressure p, fluid density ρ. In the Eulerian representation, these fluid states would be the functions of the independent variables x, y, z, and time. So vector v would be given as the function of x, y, z, and t, with the component u on the x-axis, v on the y-axis, and w on the z-axis. The pressure and the density are the scalar, so they expressed as the functions of the independent parameters x, y, z, and t. So here we examine the individual region, and we will solve the fluid states for the velocity vector, pressure, density, etc. For a specific flow, an incompressible flow, the density would be a constant. Such an incompressible flow had been widely studied and applied. For instance, the low-speed airflows past the airfoils, the flow in the ocean waves, etc. In the Eulerian representation, the fluid acceleration would be calculated as this based on the fluid velocity vector v. As we have mentioned before, the fluid velocity vector v would be the function of the independent parameters x, y, and z, and t. Therefore, we can use the chain rule of differentiation. We can obtain the fluid acceleration in the Eulerian representation given as this. And as this, here u, v, and w are the component of the fluid velocity. And this expression is called the substantial derivative. And in many textbooks, this substantial derivative is indicated as the capital D vector v over capital dt to distinguish the normal differentiation of the vector v with regard to time t. Here, we will make the explanation what is the local acceleration. This part, the partial differentiation of the vector v with regard to time. This partial differentiation can be understood at the given position p, which is fixed in the fluid domain, and the local acceleration is due to the change of the local velocity vector v from time t to time t plus delta t. Thus, the local acceleration is given as this partial differentiation with regard to time. This means when we calculate the partial differentiation, the parameters x, y, and z are kept unchanged. Here in this slide, we will look at the convective acceleration, these three terms in the substantial acceleration. So we can see when the fluid particle moving from one place to another place, that p at the position x, y, z at time t move to p prime. The position is defined as x plus delta x, y plus delta y, and z plus delta z at the time t plus delta t. So on the fluid path line, the velocity component u, v, and w would be given as the partial differentiation of x with regard to t, y with regard to t, and z with regard to t, respectively. Now we look at the expression for the convective acceleration. The partial differentiation of vector v with regard to x is the gradient of the velocity vector v in the x direction along the path line. Therefore, the partial differentiation vector v with regard to x times delta x would be the change of the velocity vector along the path line due to the change of x. And the expression partial differentiation of vector v with regard to x times partial differentiation of x with regard to t would be given as the limit of the expression as this when delta t is close to 0, and this means delta x would be close to 0 too. So this expression is the acceleration vector along the path line due to the change of x. So similarly, the other two terms, this and this, would be the acceleration vectors along the path line due to the changes of y and z. In here, we will look at the dynamic equation in the Eulerian representation. Take a small fluid region of volume delta v, see here, and we suppose the fluid velocity is expressed as the vector v the density would be rho. Thus, the dynamic equation would be given as this based on the Newton's second law of motion. This is similar to this dynamic equation for the Newton's second law of motion. So we can see rho delta V would be the mass of the fluid in the small region. And the substantial derivative vector V with regard to t would be the acceleration of the fluid in the region. And the vector Fb is the body force. In many applications, the body force would be the fluid gravitational force. And vector Fs is the surface force. And in most applications, the surface force would be caused by the fluid pressure and the fluid viscosity. And this dynamic equation for the fluid can be expressed as this. Here, the details of the substantial derivative is used for the acceleration. And the force expressed as the vector Fb and the vector Fs. Here, vector Fb is defined as the vector capital Fb divided by rho delta V, and the vector Fs is defined as the vector capital Fs divided by rho delta V. So vector Fb and vector Fs are the forces per unit mass. However, the fluid dynamic equation should be given as this in principle, since this is following the more general dynamic equation for the Newton's second law of motion. Here, in this expression, m can be a variable. That means, in this expression, the density rho can be a variable. Of course, if the fluid is incompressible, rho is a constant, then this expression and this expression would be same. But in reality, this expression is correct rather than this one, even for the compressible flow. The reason for this, if we use this dynamic equation, the derived dynamic equation is actually accepted and validated. And also, the dynamic equation would be same as that from the Reynolds transport theorem. In this slide, one more explanation would be discussed why this expression is correct. This is based on the discussion from the book The Navier-Stokes Problem in the 21st Century. In the substantial acceleration, there would be two different velocities. One is the velocity vector v. The fluid volume velocity is the velocity we discussed before, while we have another velocity vector vm with the component um, vm, and wm. This is the mass transport velocity. And in the reference, these two velocities would be different, and the expression can be given as this. And we can see if the density is a constant, then this part would be 0. The volume velocity and the mass transport velocity would be same. If the flow is compressible, so this part would not be 0. Thus, there will be difference between the vector v and the vector vm. Why is this? In my opinion, this is still not well accepted, and I didn't find out how the k can be linked with the fluid dynamic equation. Now in this slide, we'll have a look at the body force. In here, we consider the fluid gravitational force as the only body force acting on the fluid element. In the given coordinates, the gravitational force would have only one component on that direction, given as capital FBZ equaling to minus rho g delta V. Delta V is the volume of the element. Minus here is because the gravitational force is in the opposite direction with z-axis. And obviously we can see the gravitational force on x-axis and on y-axis would be 0. Hence, the body force per unit mass would be given as Fbz equaling to capital Fbz divided by rho delta V. So it is minus g. G is the gravitational acceleration. And the body force on x and y direction would be 0. If we write the body force, the gravitational force in a vector form, it would be given as this: capital vector Fb equaling to minus rho g delta V vector k, or vector Fb equaling to minus gk. Here, k is the unit vector for z-axis. In the next two slides, the surface force due to the pressure will be examined. The same cubic will be used as in the previous slide. First, we look at the y direction. The surface force due to the pressure on the fluid in the small region is calculated as this: capital Fsy as this. Here, if we take the pressure P at the center of the cubic, and we can calculate the pressure at both sides. On the left-hand side, it would be P minus the partial differentiation P over y times half delta y. And the area would be delta S1 equaling to delta x delta z. And this term is the pressure acting on the surface on the right-hand side. So this would be calculated as this, and then we have the expression for the surface force in the y direction on the cubic given as this. And based on this, we can calculate the corresponding force per unit mass given as Fsy equaling to capital Fsy divided by rho delta V. This would be given as minus 1 over rho partial differentiation P with regard to y. Here we can see rho delta V is the mass of the fluid in the cubic. In the same way, in the z direction, the surface force due to the pressure would be calculated as this. So the first part is the pressure acting on the bottom surface that has 2. And this part is the pressure acting on the top surface that has 2. The minus here means the force due to the pressure on the top surface would be in the opposite direction with z-axis, while the force due to the pressure on the bottom surface would be in the same direction with z-axis. So the force would be calculated as this and this. Similarly, the corresponding force per unit mass would be given as Fsz as this. Similarly, the force per unit mass on x-axis would be calculated as this. In this final slide, I will put all this together, the moment equations for Euler equation. We have the expression for the moment equation, and we obtain the body force and the surface force due to the pressure. The moment equation on x-axis would be given as this, and the body force component, surface force component on x-axis. As we have shown in the previous slides, the body force on x-axis would be 0. Therefore, we can put the surface force due to the pressure in the moment equation as this. And similarly, on y direction, we have the moment equation given as this, and the body force on y direction is 0. Therefore, this moment equation would be given as this. Here, the surface force due to the pressure on y direction is calculated. Similarly, in z direction, the moment equation would be given as this. And we also put the fluid gravitational force as the body force and the surface force. So we have the expression as this. Here, minus g is the body force. G is the gravitational acceleration. Minus sign here means the gravitational force is in the opposite direction with z-axis. Now, put all this together, the Euler equation would be given as this 3-moment equation. And we can see from the moment equation, we have 3 moment equations, but we have 4 unknowns: the pressure P and the 3 velocity components U, V, and W. So the Euler equation only be complete if the continuity equation is applied, even in the incompressible flows.